welcome back student. Now today we'll discuss about that cooling load estimations. We already discussed in the previous lecture video that there's in various ways we can calculate the cooling load estimate. Okay, actually cooling load, and as you know that what is cooling load? Actually the amount of heat extracted from the room or from the space to be air conditioned. So that amount of heat extracted by means of air conditioning method or air conditioning, that amount of extracted amount of heat, which amount of heat extracted from the room is basically the effect of cooling. If you reduce or if you extract the heat from any substance, then the substance is to be cooled within some times. So in the same principle, the air conditioning also works. So because there are in various ways the heat can be absorbed within the room, so we have to just consider or we have to calculate in which the room is to be hot. Okay, so that amount of temperature that gained by the room in various ways, you have to calculate all those things. Okay, so when you calculate the cooling load estimation, first of all you have to calculate the solar heat gain. Okay, solar heat gain. Now solar heat gain, as you know that when you calculate this cooling load estimation, there are main two components are there, that is sensible heat gain and another is latent heat gain. In this actually two components are there. So there is various way you can heat, or the room is basically the sensible heat gain is done by sensible heat gain, as well as there's in very way there's so much very way that the latent heat gain also is done. Now solar heat gain that is sensible through outside wall. So as you know that the ray that comes from the sun, that basically heated up the outside wall or roof. So that temperature, that air temperature, that wall temperature, roof temperature is absorbed by the wall or bricks. Okay, now transmission of heat, the wall exposed to the outdoor and the roof is not steady due to the variation in the outside air temperature and solar radiation intensity over 24 hours. Because the solar intensity is very important considerations part when you calculate the cooling load estimations. So solar intensity is depending on the time in which the intensity of the radiation, the heat or temperature air is coming out from the solar and it falls up onto the roof or outside the wall. So that is not same throughout the day. That is different due to the variation of its solar intensity power, as well as there are some temperature difference also depending on the throughout whole day. So from 6 a.m. of a particular day, from 6 a.m. to or on the another days after 4 p.m. means 4 a.m. There is so much variation in the temperature difference, because in a 6 a.m. We can get around the temperature in summer occasion that it may be at around 28-27 degrees Celsius. Okay, when it reach up to 12 p.m. or 2 p.m. on that day, the temperature can be increased up to around 40-45 at maybe or 50 degrees Celsius depending on the circumstances or condition. So the temperature difference are there. It is also depend on the solar intensity power. Intensity means intensity of the solar radiations. If the intensity of the solar radiation and the direction in which solar radiation comes from and it falls upon your roof or outside walls, it depend on that. If it is at very high radiation angle up there, solar intensity angle up there, they will fall upon your wall or roof. So obviously the amount of heat absorbed through the wall by means of wall or roof is very high quantity. But that in that particular time, they will just absorb, not released. After some time or in the evening part of the day, they will release the heat within the room. So there are two curves up there in which you can get idea that there are temperature variation up there, temperature variation throughout the whole day. Due to the temperature difference and the solar intensity power, there are two curves up there. because there are actual instantaneous load from outside, which is comes from the outside instantaneous time at which the solar intensity power is coming out from the sun. That curve is in the upper portion of the curve. The lower portion of the curve actual load instantaneous inside the room, in which you can see that. So this is the curve. So this is the curve. So this is the curve. This is the curve in which in x-axis it indicates the time. The time that from 6 a.m., 10 a.m., 2 p.m., 6 p.m., 10 p.m., 2 a.m. and 4 a.m. So in which you can see that when the radiation comes out from the sun, they will fall onto your roof or outside wall. So obviously the temperature will be increased in which the time will go on. So obviously at 2 p.m. they will pick up at the maximum instantaneous load from the outside, and it will fall down at around 6 p.m. is lower, but the negative is indicate that the temperature falls down at around 10 p.m. the curve will be diminished, because there is no as such temperature increase at all from the outside, from the air temperatures. They will at the particular time they will in this curve indicate the actual load inside room. So this is the actual load inside room. So when we reach at temperature at the time of 6 p.m. around 7 p.m. the temperature of the room is now heated compared to the outside temperature, right? So that's why in this curve it indicates the actual load inside room. So this difference is actually same. So in the upper portion of the curve means from 6 a.m. to at 6 p.m. and 6 p.m. to 4 p.m. the shaded area under the curve is same, but the difference is that there are some variations. You have to consider all those things when you calculate the cooling load estimation, because you have to calculate the amount of heat generated or amount of heat produced by the means of solar heat through outside wall. So that is basically depend on the solar intensity power as well as the time in which the maximum heat gain through the wall, okay, and in which time the temperature is very much high in a particular room. And what is the cost? The cause is that at which temperature means at the particular situation the storage capacity of the bricks or wall or the roof are there. At the evening time of the generally at the evening time of the day they will release the heat. They will release the heat in which actually the amount of heat absorbed in the whole day from 6 a.m. to 6 p.m. around they will release the heat after 6 p.m. So that's why the outside temperature of the room at 6 p.m. beyond 6 p.m. is less compared to the room. Okay. So in this way you have to consider all those things, and it also the storage capacity of heat is basically depending on the thickness of the wall, the material in which the wall is constructed, okay, and the amount of area of the wall, and actually there are some convenient way that taking into account that there are lagging effect of storage and the solar radiation to use an equivalent temperature differentiation. So the amount of heat that received or gained by the room, you can calculate that Q is equal to U into A into Tc. That Q basically is equal to U means overall heat transfer coefficient. A is the area of the wall or the bricks or the roof, and Tc or equivalent temperature differential. So that Tc is depending on the temperature, depending on your thickness of the wall, depending on the direction in which the solar intensity comes from, the solar intensity, the direction, the thickness of the wall, the material constructed. So Tc is depending on that, on the variables. So there are some chart, you can go through it, you can see it that the value of Tc is depending on which variables and how. So from that particular chart or from the particular that depending on the thickness the Tc value varies. So you have to consider all those things when you consider the cooling load estimations. So that basically the amount of heat received by means of solar heat gain through outside wall, that Q is equal to nothing but U into A into TC. Now U is your, as you know, that overall heat transfer coefficient, and A is the area of the wall in which you just fall the temperature of the fall, means that solar radiation comes out, and the TC is the equivalent temperature differential. So Q is equal to A into TC. You can get the value of solar heat gain through outside wall. Now another thing, the next way you can get the another way that amount of heat gain through another means by means of convection or by means of radiations, because soul air temperature. Now soul air temperature basically hypothetical temperature, first of all. Now second is that why it is used. Now it is used to calculate the heat received by outside surface of a building wall by the combined effect of convection as well as radiation. So in this case actually we just only consider there are only two heat transfer method are occurs, that is convection and radiations. It is basically hypothetical temperature. Okay. Now it is generally used to calculate the heat received by the wall, by the outside surface of the building, of the wall, by the means of effect of convection and radiation. You know that the heat transfer medium, there are three main heat transfer medium. There are conduction, convection, and radiations. Okay. Now, by means of convection method, that amount of heat received by means of wall of the building, that QC is equal to H0 into T naught minus T0 T naught S. That is basically H0. H0 basically your outside film coefficient. Suppose this is a wall, so outside is there film coefficient and the inside temperature. So outside film coefficient, T0 is your outside air temperature, and T naught S means outside surface air, means outside surface air, outside surface temperature of the building. Surface temperature of the building outside, not inside, outside. Okay. Now by means of convection radiation, you can, if you can calculate the solar temperature, that QR basically I into alpha. Now I is equal to radiation or intensity of the radiation. So the I into alpha. This is the absorptivity. It's depending on the material in which you can constructed your building of the wall or roof. Basically is basically cement or concrete are there. So obviously QR is equal to I into alpha. Okay. And alpha also depending on the thickness and as well as the material. Okay. Alpha and the angle in which the incident rate comes out. So that is the angle. This is the incident angle. Okay. That QR is basically I into alpha. So when you calculate the soil air temperature, to calculate the cooling load estimation, that will be your QoS. That will be the summation of QC plus QS. That is the heat received by the convection method and the heat received as well as the QC plus QR. It will be QR. Okay. So the heat received by the radiation method. Okay. So QAS is QC plus QR. Now in terms of QC, you can put here F0 into this term, and similarly QR is equal to, you can put this I into alpha. Now if you calculate the, or if you simplify these equations, you can get that F0 into T0 plus I alpha divided by F0 minus F0 into T0 T naught S. So this term basically your soil air temperature. So F0 into TE, that basically your soil air temperature. F0 into TE minus F0 TOS. So F0 will be common here, that will be TE minus TE or TOS. F0 is your outside film coefficient. Okay. And TE your solar temperature. When you consider the convection and radiation of the method in which the temperature can be increased by means of wall, through walls actually, minus TOS your outside surface air temperature of the wall. Okay, means outside surface temperature of the wall. So that is the soil air temperature. You have to consider all these things when you calculate the cooling load estimation. There are other various ways that you have to assume, you have to consider all these things. Okay. Now, another important point is that for cooling load estimation, that your solar heat gain through glass areas, because in a particular room or the space where it used to be air conditioned, so there it may be that the room is basically is made of is maximum portion of the room made of either glass or any other fibers also, because in the window part as well as in door part also. So it may be happen that actually it happens in which the solar radiations obviously they will comes falls into the walls or roof, but as it is the windows is made of either glass fibers modern days, and obviously doors also. So there's a high percentage of chances that high amount of heat is enter into the room because by means of windows or doors. Okay, so by this means there are some solar heat gain actually occurs through glass areas. Okay, there are maximum chances basically means of either convection or radiation method. There will be heat transfer takes place in between when the solar radiation or solar intensity takes place in the windows. It may happen that there are some part of heat is entered into the room. Okay, and by some mechanisms, it may be by either convection mechanism or radiations mechanisms, or it is, as you know, when the heat is fall means the solar heat is actually intensity of power is solar is intensity of power is fall into the glass fibers. Obviously they will form they will subjected to some of the solar radiations. That part of is obviously they will absorb it. There some part is reflected, and there some part of that transmitted into the interior surface of the building. So there are possibly three ways that the heat is transformed: either reflected, absorbed into the windows glass fiber, or it transmit to the room. But as it is, when the temperature is increased, the capacity of heat absorbing capacity of the glass fibers is the similar some limited power of there. So obviously they will release it at some part when they reach the beyond limit. Beyond that limit, the maximum amount of heat will be rejected into the room. So there possibly there are maximum amount of heat entered into the room, and due to this the major load will be applied onto the cooling load actually onto the cooling apparatus. So net actually due to this the net heat gain, that is basically the summation of transmitted solar radiation and heat flow by convection and radiation exchange between glass and indoor surfaces. But the transmitted solar radiations, it may be negligible, but the heat flow by convection and radiation that exchange between glass and the indoor surfaces, that may be, it's a summation of absorbed solar radiation by means of glass fibers, as well as that plus minus of radiation and convection heat exchange between glass and outdoor surfaces. Okay, so in this way actually we can also consider that there are some solar heat gain, that actually not some the maximum amount of chances that maximum amount of heat gain can be possible by this through glass fibers, because this through means this through this glass fibers there are maximum chances heat gain are possible. And another is heat gain due to the infiltrations. So infiltration is basically due to the, because it is called when there are some enters in the means air that enters into the air conditioned space through some crack, through some by means of gap. Okay, or the repetitive opening of doors. uh, the some amount of outside air enters into the room, because there are some gap are there in between door or in between windows, or they maybe happen there are some cracks are there. So through this channel, through this crack, through this window, through this gap, or by means of repeated opening of doors, that may be possible that the outside air enters into the room. That temperature, because outside temperature is very high compared to the indoor temperature of the room where the conditioned air condition is working. So obviously that may happen that when the temperature, when the outside air coming into the room, so obviously temperature will be increased. If the temperature will be increased, the high amount of if, there should be means high amount of power will be power will be losses will be there, because air conditioning air conditioning has to be again recycling, and the temperature should be constant within the room. So there are some unsteady condition will be occurs if there are some unconditioned air is comes into the room from the outside through windows, through channel, or through crack also. So it is basically the measurement. The measurement actually, what is the cause of that? That cause is that there are some pressure difference between two sides of the window, means outside and inside room of the window and door, and there are some wind velocity, there are directions. Okay, so there are two methods are there. One is Crackland method and air exchange method. So Crackland method, in this method actually, what are the amount of heat gain due to the infiltration, that is basically calculate that that is basically your L into W into H, means length into width into height of the room is to be air conditioned, into AC, means the crack length, okay, divided by 60 meter cube per minute. So that amount of air is entered into the room, that is basically infiltrated air, we can say that. So this air can be increase the temperature of the room where air conditioning is working. So there are some extra effort will be done by the air conditioning, there are some power loss will be there. So that's why when you calculate this cooling load estimations, we have to consider also, is there any gap, or is there any crack, or is there any repetitive opening door is or not. So there is, as much as we can consider all those things, we can get actual result also. So this is the heat gain due to the infiltrations, and obviously there is as much as there are other variables are there, so that they can impact actually into the cooling load estimations. Okay, so for today's class, up to you. Okay, thank you very much for listening and watching me, and goodbye.